my name is Mohammad, and today I'm going to be doing my presentation in English, since all the material I found were in English and it was hard to translate correctly to Spanish. Let us begin. My presentation today is going to be about laser-assisted chemical vapor deposition, or LCVD. In order to explain LCVD, I first need to explain conventional CVD. It's a technology widely used to produce coatings or thin films. It could also be used to produce high purity material in bulk or powder form. It can also be used to produce multi-layer coating on certain desired material. It is most commonly used in the semiconductor industry to produce solar panels, LEDs, and integrated circuits. How does conventional CVD operation work? Well, CVD is a very sensitive operation, therefore it needs to be carried out in an isolated chamber at a low pressure, away from contaminant. A base material called substrate, or the object we want to coat or produce the film or the desired object on, would be placed inside the isolated chamber. Then a stream of reacting gases mixed with inert or buffer gases would be pumped into the chamber. After that, an external stimulant is usually heat, could be plasma, could be lasers, as of our case, could be chemical catalyst, will cause a chemical reaction inside the chamber, which will deposit the desired material onto our object or substrate. And this chemical reaction will produce unwanted waste gases, usually toxic, that need to be pumped out. Now for laser-assisted chemical vapor deposition. Laser-assisted chemical vapor deposition is a type of CVD that uses laser beams or high-intensity lights to initiate or to drive the chemical reaction inside the chemical vapor mixture. The laser would be used to either heat up the vapor itself, or the substrate will be used to electrically excite the vapor or the gas. One of the main advantages of LCVD is that it lowers the temperature from around 1200, 800 to around 200 Celsius. Therefore, a more sensitive material could be coated. LCVD also increases the deposit rate of the system from few micrometer per hour to by a factor of 100 to 1000. There are two types of laser-assisted chemical vapor deposition. There are photolytic LCVD and pyrolytic LCVD. The main difference between the two is the way the excitation of the gas happen. In the photolytic, it happens by the gas absorbing the photon energy of the laser, which will, in this case, would normally be a UV light that will shine on the gas, causing it to absorb its energy and therefore deposit. In the pyrolytic LCVD, this type the laser beam uses laser irradiation to heat up a spot on the substrate, causing it to reach a threshold that will cause the chemical reaction and therefore the chemical deposition onto the desired substrate. This process uses usually continuous wave infrared lasers, such as CO2 lasers. The main difference between the two types is the deposition and the deposition temperature and the deposition rate and the deposition area. In the photolytic LCVD, it has lower deposition rate than conventional CVD, temperature than conventional CVD, but has similar deposition rate and similar deposition area. In pyrolytic, it has much smaller deposition area, much concentrated, but has much faster deposition rate, almost in this case 3,500 micrometers per hour. What are the general characteristics of CVD? Most metals and materials can be deposited using conventional CVD, meaning that almost 80% of the material on the periodic table has been already deposited using CVD at one point. But that also apply to pyrolytic LCVDs, since it also uses heat, but that does not apply to photolytic LCVDs, since the lasers need to produce enough photon energy to cause the excitation, and currently there's no lasers that can reach all range of materials. The CVDs, the created CVDs films usually exhibit excellent physical properties such as adherence, conductivity, hardness, smoothness, and highly oriented formation. This means that using CVDs we can add materials together, we can add characteristic to the material using the coating that didn't have before, like corrosive resistant, like scratch resistant, like conductivity. The technology is highly precise, and it needs almost no post-processing. It's almost finished material. The operation is highly controllable, since the deposit rate, which is it is constant, depends on various controllable parameters such as the pressure inside the chamber, such as the chemical reaction initiator. In a traditional CVD, it is normal heating. It could be plasma energy, it could be proton energy, photon energy. Also, another parameter is the flow rate of the gases to the chamber, and the cooling and heating of the substrate or the object. General characteristic of LCVDs. The main characteristic and the main characteristic of LCVD is it reduces it could be used to do selective deposition. That means that it could be used to technically draw lines of deposit material at the selective areas. This could mean that we could do highly controlled desired nanotubes, nanofilms, nanorods of very high value materials. We could do 3D structures or models like microsprings, like micro structures, like micro prototypes. Another characteristic that it requires more simplistic equipment than conventional CVD, just because we don't need the heating apparatus that normal CVD have, which mean no corrosion due to heating. LCVD would require only the chamber window for the infrared or for the laser exhaust and inlet equipment. Another characteristic is it has very rapid heating. It could reach, in a few seconds, it could reach 2000 to 3000 Celsius, and it has a very high deposition rate compared to conventional CVDs. And these photos explain or demonstrate selective deposition and the potential of doing it for example here for prototyping, for producing micro springs that would normally be hard to do in certain material, but with LCVD it's easier. We could also produce nanotube or nanorods of high value material. We could also use it to produce selective line deposition, to produce, for example, for integrated circuited, for repairing high value prototypes. Advantages and disadvantages. Due to the elimination of the need of high temperature, LCVD could be used to deposit amorphous films, that mean more elastic films. On the other hand, it could go to a very high temperature, which could mean that it could produce deposit crystalline silicons. LCVD also offers a high control over film thickness, uniform deposition, also high pureness of the film. All of it could be controlled very easily due to the existence of highly controllable independent parameters. And disadvantages are the presence of toxic gases, either in the buffer or inert gases, or in the byproduct of the reaction, which could not be avoided. The range of the other disadvantage is that the range of the reactive gases is limited due to the inexistence of lasers that could produce photon energy that would be enough to reach all energy levels needed to produce deposition from different material, as opposed to normal heating, which would normally reach most of the periodic table. That's it. Thank you for listening.